Welcome to the fifth part of section 1 of the limited online lectures in beef cattle breeding. You will remember that we've dealt with the mode of inheritance and special focus later on so-called quantitative traits or polygenic traits, or traits that are influenced by a multitude of genes, where the environment has an influence on the expression of the traits being influenced by those genes. We talked about heritabilities, we just mentioned genetic correlations, and then we moved on to a way, BLUP, breeding values, of predicting the genetic merit of individual animals for specific traits. In that, we looked at the extreme importance of two sources of information, the one source being the pedigree information of the animal. Why pedigrees? Because animals that are related share common genes or parts of the chromosome with the genetic code on it, or the genotype. So that's very important, because if you then add the second source, namely the recording of the traits, call it production traits if you like, or performance traits, even reproductive performance traits. If you add that second part, it means that the performance of the animal in specific environments and very specific contemporary groups. Contemporary group is basically something that levels the playing field so that you can really compare animals in terms of the expression of the traits that you are considering to select for. So that when you measure that in a specific contemporary group, let's say the progeny or the other family members of an animal, and you know what the relationship, genetic relationship of a specific animal is with his family members, it enhances the accuracy of your prediction. So we had a special focus on the value of a contemporary group and why it's so important that you define your contemporary groups correctly, not to have preferential measurements of animals. You must measure all the animals on the farm, but if there are specific animals that got a different type of treatment than the others, those animals need to be separated in separate contemporary groups. We also handled the example of a sick animal or an animal that had some difficulty in growing, or whatever the case might be for that trait, to exclude those animals from your contemporary groups. Also, the importance to have the progeny of more than one bull in a specific contemporary groups, otherwise you don't have a comparative base to compare those bulls with each other. And then obviously we also emphasized the value of a so-called link sire, and how BLUP breeding values actually uses link sires to connect or compare different contemporary groups or different farms or different seasons with each other by means of so-called link sires. A link sire not necessarily need to be the same sire. It can be two sibs, let's say two half sibs, two brothers, half brothers, who share 25% of the same genotype. That could also then serve as a link sire in that case. So let's move on to part 5 then. We are again looking at breeding values on a broader scale, and maybe just a little bit more on a practical level. Just a reminder, we're talking about BLUP. BLUP is the methodology that is being used to calculate the genetic merit or to predict the genetic merit of each animal. So BLUP is an acronym for Best Linear Unbiased Prediction. So it's linear models being used. Obviously, it's the best methodology available to predict the genetic merit of an animal. Even in the era of genomic selection, BLUP is still being used. So there's sometimes a misconception that the inclusion of genomic information has done away with BLUP. We're now using BLUP more than ever. prior to the genomic era. So it's the best methodology available, it's linear models being used, it's an unbiased way of predicting the genetic merit of an animal. It's unbiased in the sense that irrespective of your preferential matings, please note matings, preferential matings, there's an unbiased answer to the genetic merit being predicted. And it's a prediction. You predict the merit of an animal, the progeny, how much better or worse the progeny of an animal will be in comparison with the progeny of other animals. So it's basically then the method to separate genetics from the environment. So how much of these differences that we measure or record are due to the genetic differences amongst the animals as opposed to the environmental effect. So in some instances they would say it's separating feeding from breeding. An EBV, I've mentioned that, is a so-called estimated breeding value. That's the value that's been assigned in terms of the outcome of the BLUP methodology being used. So I've also mentioned the most important equation in animal breeding is P equals G plus E. So the performance or the phenotype or the looks or the calving interval or whatever trait you measure is basically made up of the genetic differences amongst the animals plus the environmental effects on the expression of that trait. So in terms of the genetic part, this is basically what we then predict with our BLUP breeding values. So the EBVs indicate the genetic merit of an animal for a specific trait. Remember, the fact that you calculate breeding values for a specific trait doesn't say much about your breeding objectives. In section 2, we will deal with breeding objectives. Here we're dealing with methodology. Methodology should be separate from objectives. Objectives is something else. My objective can be to breed smaller animals, fatter animals. My neighbor's objective could be to breed bigger animals, leaner animals. So the objective, but we will measure the same traits. So it's how you use those traits in your objectives that matter. So section 1 deals with the methodology of breeding value predictions rather than the objectives or the breeding objectives. That was just a side note on breeding objectives versus methodology. So this is typically what would be available to a breeder or a buyer of an animal. This is just a little block from a science report from one of the breeds. There's an animal, let's call him A92202, so it's an animal born in 92, and it's a 282nd animal born in this specific herd, herd A. There are basically three things written into this little block. The top left one is the breeding value in the unit of measurements. So if you measure your trait in kilograms, your breeding values will be in kilograms. If you measure your trait in days, like calving interval or age at first calving, your breeding value will be in days. If you measure your trait in millimeters, let's say fat depth on the subcutaneous fat, your breeding value will be in millimeters. So as a first thing, your breeding values are expressed in the unit of measurements. Then there's also a so-called accuracy. In certain instances they call it the reliability. For example, in the dairy industry, there's an accuracy associated with that prediction. Now, in short, and we'll talk about accuracies a little bit more, in short, it means how much information was available when this breeding value was predicted. Was it just based on pedigree information? Was the animal actually also weighed or measured for the specific trait? How big was the contemporary group where it was weighed in? What is the heritability of the trait? The higher the heritability, the more the actual phenotype or measurement reflects the genetic differences amongst the animals. Is it an old bull with a lot of progeny? So obviously then it pushes up the accuracy of your prediction if you know more of how the animal actually breeds. So the accuracy is then a reflection of the amount of information available when this prediction was made. And then, and we'll talk a little bit about this, at Studbook we also express these breeding values, the 7.5, in terms of what we call a breeding value index. And I will talk a little bit more about that. Just in short, 100 breeding value index depict the average of the animals currently alive in a specific breed. So an average animal will have 100, and then you have a spread away from 100. If an animal has a higher breeding value, it will be over 100. If it has a lower breeding value compared to the average of the breed, it will be lower than 100. So in short, what is a breeding value? It's an indication of the animal's genetic merit. Its merit as a parent. It's also then the expected advantage or disadvantage in performance compared to the performance of the progeny of other breeding animals. So it's always a comparison. Each and every breeding value would be relative to the breeding values of other animals, either the rest of the breed or two bulls that you compare. And it's then obviously an indication of how much of its performance relative to other animals will be transmitted to its progeny. Coming back to the breeding value index, you remember the little block we had. There's this animal, it's got a breeding value of 2.1 kilograms for, let's call it weaning weight in this instance, with an accuracy of 72% and a breeding value index of 104. So the breed average for this would be pinned down on a 100, and this animal then has 4 index points higher breeding value than the average of the breed. So he's superior or heavier, he will breed heavier progeny at weaning compared to the average animal in the breed. So it's a very easy way of interpreting it, because otherwise you need to know what the average of the breed is if you only use the breeding value, the kilogram breeding value. So it's fairly easy to just use this so-called breeding value indices to assist you in ascertaining whether an animal is actually above or below the average value of the breed. An index of above 100 is in most cases, but not always. In most cases it's an indication of the desired direction that you want to select in. In some cases it might not be, and we'll talk about that as well. This is an example where, for example, the average could be more acceptable than the extremes. So in certain cases, some farmers would tell you, let's say for birth weight, for example, they would rather select for an average birth weight than an extreme towards the lighter side. The lighter side would be in birth weight, it would be on this extreme. Then they would rather select for an average. In other cases, farmers would say that they would like to select for extreme values, like feed conversion ratio, for example, or the fertility traits. You would go for the extreme, the most fertile animal, and you would also select for the most efficient animal in terms of cow efficiency, for example. So the acceptable range in this case could be then towards the extreme, whereas certain traits or properties, an average animal between, let's say, 80 and 120 index points would be the most desirable animal to select for. Just a few words then on accuracy. Like I said, the more information used in the estimation of the breeding value, the higher the accuracy. So if you, for example, if only one parent is known and the animal wasn't recorded yet for the trait that you're predicting the genetic merit for, the accuracy will be extremely low, especially for traits with a low heritability value as well. As soon as the animal is being, the parentage is being cleared out with DNA testing, the accuracy will go up a little bit. As soon as the animal is actually recorded for the trait, the accuracy will also go up. And as soon as more, let's say more of the sire's progeny is also known and recorded, the accuracy of the sire will go up, but the animal's own accuracy will also then increase, because there's an increased value of prediction or accuracy of prediction. And obviously, as soon as that animal produces progeny with records, the accuracy will also increase as well. So the accuracy is basically expressed as a value or a percentage value between 0 and 100%. Obviously, no animal can ever get to 100%. It possibly can get to 99.9% or whatever the case might be. So here's just an example of breeding value for birth weight minus 0.09 kilograms. So this animal and it's 102, so that's 102 index points higher than the average of the breed. We twist the breeding value for index around for birth weight, so it means the lower the birth weight, the higher the index. So this specific animal will breed lighter calves at birth, 2 index points lighter than the average of the live animals in the breed. And in this instance, for example, this accuracy is already at 81%, so one can use this breeding value with confidence. This is another example. Cow fertility, 2.8 days. That's calving interval. So it's actually longer than the others, so that gives you a lower. This is not very clear, but it's 85%. So that's 15 index points below the average of the breed. That means worse calving intervals. This animal will breed worse calving intervals than the average of the breed, but at this stage it's based on a very limited amount of data or information, and only a 17% accuracy. So you have to use this with caution, or this specific animal or this breeding values with caution. So in essence, what the accuracy tells us, from one prediction to the next over time, it could happen that you predict that this breeding value is, let's say, 108 today, but it's an extremely low accuracy, and as soon as you get more and more information in, it could mean that your prediction will change over time, because you have more information for your prediction. So the accuracy tells you about the probability that your predictions might change over time. So if you have a very high accuracy, your chances of the prediction to change is very slim, so it's in a very narrow band. But if you predict with a very low accuracy, it's got a broad band. It can change over time as you get more information in to predict the genetic merit for that specific trait. This is just a general rule of thumb in terms of levels of accuracy. With the accuracy of below 20%, you have limited information, and obviously you should use that with caution. Between 30 and 50%, it's usually when there's additional pedigree information and the pedigree or the parents have a reasonable accuracy in their predictions, and the animal has its own measurements. As soon as progeny measurement kicks in, then obviously the accuracy will increase, and then you can use those animals with more confidence. This might not be practical if you go to a sale and you buy a 2.5-year-old bull, 2 or 3-year-old bull. For certain traits, the accuracies can still be very low, especially on female fertility, for example, because you cannot measure female fertility on a bull. You can't measure age at first calving or calving interval on the bull, or the maternal ability, the milk cannot be measured on the bull itself. So on certain traits and properties, the accuracy might be nearing the 60s, but for other traits, there might be limited information available, and then you have to do with what you have in terms of making a choice when buying such a bull. Okay, so I think this is basically what I have said. If it's below 40, there's some risk involved. Between 40 and 80%, the risk is much less, and over 80%, the risk is fairly low. It's just basically a risk indicator rather than anything else. Don't select on accuracies. Select on breeding values, but use accuracies as a means to know what your risk is when you select. Okay, so just getting back to breeding values again, this is the actual EBVs in kilograms. You will see in this case we're talking about birth weight as an example. So the expectation is that a calf born will have a so-called what we call a parent average or a mid-parent value. So if the bull's breeding value prediction is at plus 4.4 kilograms, 4.4 kilograms heavier than the so-called base year, and the dam's at plus 2.2 kilograms. If you add those two up and you divide by 2, you expect the calf's breeding value to be 3.3 kilograms. That's an expectation. But remember, there's a random effect when the sperm and the eggshells are formed, and that means that this is an expectation. So if you do this 100 times over, you will end up at 3.3 kilograms. But obviously, you can only have one calf from a single mating, except if you have embryo multiplication and you artificially inseminate animals with that, or you have embryo transfers. But generally spoken, you expect that, and as soon as the calf is being weighed at birth, it will tell you what the deviation is. Did it get the good or the bad genes from the parents? Where does it fall into this expected average, or away from this expected average from the two parents? So the same thing would then apply for the breeding value index. If you have an 80 cow with 120 bull, you expect 100 calf. But it never happens like that. Just that's on average what is being expected, and just by the throw of the dice, the randomness of sperm and ova being formed, the calf can even be higher than the sire or lower than the dam. The chances are just the biggest that it will be on average, will be on parent average. So let's look at a few test matings. We have this cow, and you have a choice of two bulls to use on this cow. So the cow has got a breeding value index of 108, and our first bull 79. So if we do a mating from this bull on this cow, you end up with and the average of their calves will only be a 94. So you will see that you're actually breeding backwards in this case by choosing the wrong bull. As opposed to another possibility where let's say it's bull 2 here, and you use 116 bull on this cow, and if you work out the average, you'll end up at 112. So basically you're breeding forwards then by picking the right bull. Here are the same figures in terms of the breeding value prediction in kilograms. 14.7 and a -2 would then give you on average a calf of 6.4 versus in this case an average calf of 16.3. So this is basically how selection works. Cutting off the lower tail end of your females, but selecting from the top end of the bulls that's available not just in your herd but also available in the breed. Because now we have ascertained that you can compare animals in the whole breed due to blood breeding values, making use of the fact that you start with your contemporary groups, you have your pedigree information that links contemporary groups together, you have some link sires, you've taken it into account that not everything that you observe or measure on the animal is transferable because of the heritability estimate. It's just the part that's due to the genetic differences amongst animals. Okay, so basically this is what you expect from the two bulls progeny. You'll always although you will, even from the worst of the two bulls, you will find that some of its progeny will actually outperform a lot of the progeny of the better bull. So irrespective of what the breeding value tells you, there's also a variation around a mean in terms of the progeny performance. But you can see on average, this bull's progeny will outperform that bull's progeny, our second bull. So, I think this is a very important concept to also note, is that don't expect every calf of the better bull to be better than all the calves of the worst bull. There's always a variation as well, as in this case. What causes variation? This is just depicting a chromosome, the two chromatide strings of a chromosome. Remember, it's a double helix, so this is just a depiction of that. We're dealing with a multitude of genes, so-called additive genes. You have to add the value of each gene up, and that gives you the breeding value. So this is an example where you have a +2 kilogram gene, let's say for winning weight, and a +4, so that already gives you a +6 breeding value, and a +10 and a -10, so the net effect here is 0, and a -5 and a +5, the net effect here is a 0. So when sperm is formed, this actually rips open, and one part would go into one sperm and the other one would go into another sperm cell when sperm would be forming. What also happens is that, so in this case, if this was formed, you will see that just by chance in that sperm there will be a +2, +10, that gives you a +12, -5 value. So that sperm's breeding value will be different, or the potential will be different to this one that's a +4, -5, -10, +5. So the net effect is different. What can also happen while sperm is formed is what we call crossing over. So a little part would break from the one to the other, and you end up with a completely different sperm. So this bull can produce a -3 or a +9 sperm, and that's the way nature works in terms of creating variability all the time. You can also have two crossovers, so in this case this sperm will have a -13 and a +19. Same bull, different, and we know there's a multitude, there are millions of sperm, and anyone's got an equal chance of fertilizing the ovum or the eggshell as well. I would like to also dwell a little bit onto genomic selection. Genomic selection is what's happening in the world nowadays, where information from the genome of the animal is actually added to blub. Remember I said earlier on, in the era of genomic selection, blub is becoming more and more important, not less. There's a saying, it's coined to a professor at the Scottish University, that says that in the era of genomics, phenotype is king, or queen if you like. So it's becoming more and more, Mike Coffey, his name is Mike Coffey, it's becoming more and more important to measure and to use this information. So what the genomic information will assist us with, or is already assisting us with, is if you look at the accuracy of specific traits, such as sex limited traits, that's age at first calving, calving interval, you can only measure it on females, or you look at milk production, even in beef cattle, maternal ability. It means that with the current blub evaluation, where you have pedigree and measurements, you might jump up to an accuracy of about 30%, and as soon as you get offspring being recorded, your accuracy of your prediction will start rising, let's say to 60% or beyond. With genomic evaluation, if you genotype this bull early in life, and you add the additional information from the genotype information, which in essence tells you how related, genetically related he is to other animals in the population with high accuracy values for the breeding value prediction, then the accuracy will actually jump up earlier on. So you end up with an accuracy basically with the equivalent of, it depends on the trait, of 10 progeny already being recorded. So earlier in life you can make informed decisions with genomic selection in this case. What basically happens with the so-called single step that we use at SA Stud is that traditionally in a pedigree information you used the 50-50, 25-25 for, remember when we talked about pedigree information in terms of relationships of a specific animal with his dam sire and grandsire dams. What genomic pedigree does is it actually looks at the code at the genomic level and see how related the specific animal is to some of its predecessors or other animals in the breed. So that assists us where you have, for example, if you have a grandparent that's highly accurate for a specific the prediction, genetic method prediction, that is being, and you can see the genetic or the resemblance of this animal with its grandparent, then obviously it enhances your prediction accuracy as well. I would also like, and this comes from some of the questions we get from farmers, to make to give you an example of two half brothers of this bull that weighed exactly the same in the contemporary group. They both weighed 41 kilograms at birth, but you can see they have vast difference in their breeding value prediction. The breeding value index in this case of this young bull calf is 74 and that one is 110. But you will see that what happens is that and I think it's sometimes not realized from farmers, is look at the two cows that this bull was being used on. This cow had a breeding value index of 129 and that 177. So basically, although these two bull calves weighed exactly the same in their contemporary groups, we also know that they share 50% of their genes with their dams, and that, so the blood breeding value realized that or used that in the prediction, and that's why there is such a vast difference in the prediction. The interesting part is if we go beyond this and look what happened with the progeny of these two bull calves. They were both being used in different herds and different contemporary groups. You will see that in the first instance, this bull in 8 of the contemporary groups, this bull produced heavier calves at birth than the average of those groups. So it was a true reflection. The prediction was a true reflection. In one group, he produced an average, and then in one group, only in one group, the birth weights of his calves were a bit lighter. So it just shows you that the prediction was spot on. In terms, although they weighed the same in the contemporary group, it remembers, the system remembers that it actually shares genes from a dam that was prone to give heavier calves at birth. The second bull, only in 5 groups he did give heavier calves, but in 8 groups his progeny were lighter than the average of the progeny of other bulls, and in one group on average. So this is just to show that prediction is much more accurate than the actual birth weight being used as a selection criteria. This then brings us to the end of part 5 of section 1 of the limited online lectures in beef cattle breeding. We look forward to having you in the last part 6 of section 1. Good luck.